In this lesson, we're going to continue performing equilibrium calculations while making some simplifying rules to decrease the complexity of our calculations. Let's begin. Sometimes when solving equilibrium problems, you run into complicated expressions to find the value of x. In this case, you can simplify the calculation by eliminating any x that is added or subtracted to a value, but you may not eliminate an x that is multiplying or dividing a value. That may seem hard to understand right now. We'll come back to that later. Before we make a simplification, we need to check what's called the 100 rule. If the following expression is much greater than 100, then we can perform the simplification. So we take the initial concentration, we divide by k, and if that is greater than 100, then we can perform the simplification. The reason this works is that if the equilibrium constant k is very small, then you will have very little reactants form products. So if k is very small, there is a very small shift to the right. Okay, it won't actually shift to the right very much. So the x value, the change value, will in fact be very, very small. We have to make the statement about the assumption that we're making and the simplification we are applying. And then at the end, we have to justify our assumption by showing that it gives less than a 5% error or 5% difference. And finally, your Q value at the end of all the calculations should be close to K. If the 100 rule doesn't work out, we cannot perform the simplification. So again, these steps might seem a little complex right now, so let's go straight into a calculation to see how we will apply these steps. So, example 1, for a specific temperature, the K value for carbon dioxide decomposing into carbon monoxide and oxygen is 6.4 times 10 to the negative 7. So when I read that, I see, okay, 6.4 times 10 to the negative 7, that means there will not be a shift right very much in this reaction. So that means that very little of the CO2 will in fact decompose into CO and oxygen. I cannot say that no carbon dioxide will decompose because there is some value, but given the K expression, or the K value, it's going to be pretty small. So we need to find the equilibrium concentrations of all the entities. So I need the equilibrium concentration of carbon dioxide, carbon monoxide, and oxygen if I start with 0.25 moles of carbon dioxide in a 1 liter closed container. So I begin this calculation by writing out the chemical reaction. And the chemical reaction here is carbon dioxide gas is in equilibrium with carbon monoxide gas and oxygen gas. Okay. I balance the reaction 2 and 2. Given the K expression right here at 6.4 times 10 to the negative 7, again, I know that very little of the CO2 will in fact decompose into carbon monoxide and oxygen, however some will. I now write out my ice chart. And so my initial concentration of carbon dioxide is 0.25 moles divided by 1 liter. So that's actually quite easy. That's just 0.250 molar. I'm given no initial concentration of carbon monoxide and no initial concentration of oxygen. So that means that the equilibrium system, it's not at equilibrium yet, and it's going to shift right. When it shifts right, we're going to get a plus x here, but because the stoichiometric coefficient is 2, I'm going to get plus 2x over here, and over here I'll get minus 2x. So that at equilibrium I have 2x, I have x, and I have 0.250 minus 2x. Again, I know that this system is not shifting right very much because of the small K value. So these x values will in fact be very small. But I'm going to calculate them anyway. And it is asking for the equilibrium concentrations of all the entities. So I'm looking for these equilibrium values right here, which means that I need to solve for x. So in order to solve for x, I need to come up with an equation. And so I'll do that by writing out my equilibrium law, which is K is equal to the concentration of CO raised to the power of 2, concentration of times concentration of oxygen, all over the concentration of carbon dioxide. And that is also raised to the exponent 2. I have the K value because that was given to me in the question. The K value was 6.40 times 10 to the negative 7. The CO value at equilibrium, is 2x. So 2x, and that's squared. The equilibrium value of oxygen is x. And the equilibrium value of carbon dioxide is 0.250 minus 2x squared. So if I expand the numerator just a little bit here, it will show why this becomes a complex calculation. By expanding the numerator, 2x squared is going to be 4x squared, then times x, all over what will become a relatively complicated binomial squared. And so I end up having 6.40 times 10 to the negative 7 is equal to 4x cubed all over this binomial squared. So in this equation here, I will have, as you can see here, a cubic. And I'll have a cubic with multiple terms. That is going to be a challenge to solve. So what I'm going to do is I am going to make a simplification. So here's my simplification. I'm going to check the 100 rule. And just to recap what the 100 rule is, let's go back up here. The 100 rule is I take the initial concentration over the K value and see if it's greater than 100. If the initial concentration is very high in comparison to the K value, then I can make the assumption that X is going to be very, very small. So let's check the 100 rule. So I'll just rewrite it over here so you have it in your notes. It is initial concentration all over the K value needs to be greater than 100. So my initial concentration in the question for carbon dioxide was 0.250 molar, and my K value is 6.4 times 10 to the negative 7. So 0.250 divided by 6.40 times 10 to the negative 7 is greater than 100. And when I go to calculate this value out over here, I get, looks like I get 390,625. And that is, in fact, much greater than 100. So I'm able to make the following assumption. That tells me that this X value, which I already knew was going to be very small, is going to be insignificant in comparison to the 0.250. Because it is so small, I can ignore it. And we talked about that right up here at the beginning of the lesson. I can eliminate any X that is added or subtracted to a value because it is extremely small. The X value, as we said here, is going to be very, very small. So I can eliminate it. I cannot, however, eliminate any X that is multiplying or dividing a value. So what I will say here, this is my assumption. Okay, so we say therefore, and you must include this, we assume that the following: 0.250 minus 2x, I'm going to eliminate this. So I will say is just approximately equal to 0.250. Because this x is so small, when I would subtract it from 0.250, the number I would get is still basically 0.250. So I'm just going to keep 0.250 to simplify this calculation here. Okay. So with this simplification, I'm going to go back to this portion of my calculation right here, showing you right here, 6.4 times 10 to the negative 7. So I'll say, therefore, 6.40 times 10 to the negative 7 is equal to 4x cubed. Now I can't get rid of that x because it's being multiplied by a value and it's being cubed, so can't eliminate that. But what I can say now is that this 0.250 minus 2x is just basically 0.250 squared. And that has to be an approximation, right? So I need to keep this dot above the equal sign here because I have made an approximation to make my life a little easier. And then when I go to rearrange things, I end up with basically 6.40 times 10 to the negative 7 times 0.250 squared is equal to 4x cubed. And then, again, this is an approximation, so I'll keep the dot above the equal sign. And then I solve for x by dividing both sides by 4 and then taking the cube root. Okay, so that's just a mathematical manipulation. And I get that, so therefore, x is approximately, again, it's an approximation, equal to 0.00215. So I have now achieved a value of x using my simplification. Right here, I've achieved that value of x here, I have it over here. And so now what I need to do is I need to just check to see that my simplification is valid. So I'll do what's called a 5% rule. So the 5% rule looks for the difference in the values, right? So it's the difference to see if there's a 5% difference. So I'll do it with the assumption, okay, so I go 0.250. That is with the assumption that x is insignificant. And then I subtract that with, if I did not make that simplification, so 0.250, okay, minus 2, and I will insert the value of x, 0.00215, okay, all over the average of these two numbers. So here we go, 0.250 plus 0.250 minus 2 times 0.00215 divided by 2. Okay. So the difference with the assumption, without the assumption, over the average of the two values times 100%. And when we go to calculate that, what we find is we get approximately 1.7%, which is less than a 5% difference between the two values. So therefore, the assumption is valid. Similarly, I can do a Q calculation at equilibrium, and at equilibrium, right, so I'm just using these right here, my carbon monoxide value would be 2 times 0.00215 squared times the x value, which is 0.00215. And I'm going to include my assumption, which is that in the bottom I just have 0.25 squared, right? I'm assuming that no x is taken away from this value because x was exceedingly small. And I get my Q for that, and I get 6.39 times 10 to the negative 7, which is approximately equal to the K value that I was given in the question. So that tells me that using the assumption that I've made, I have been able to input that into equilibrium law and get the K value. So again, these two checks show that the assumption is valid. So at equilibrium, now this is my final answer, I can now insert the value of x into these equilibrium expressions here and find out what the equilibrium concentrations are. So I'll write at equilibrium remember, I can assume that the concentration of CO2 gas is approximately equal to 0.250. I'm going to assume that that the subtraction of the 2x is insignificant. So it's basically the same concentration I started off with, right? I mean, there is a small difference, but it's not enough to report. My concentration of carbon monoxide, though, is given as 2 times x, right? So 2 times 0.00215. So my carbon monoxide concentration is given as 0.00430 molar, and my oxygen concentration is given as approximately 0.00215 molar. So, just to recap with these questions, we start by making a chemical equation, an equilibrium equation. We balance it, we make our ice chart, and then we proceed to fill in the values of the ice chart. We write the equilibrium law. We insert the values given from our ice chart, as well as the K value given to us in the question. And then we expand until we get to a complicated portion here. We check the 100 rule. If the 100 rule works out, then we can say that this subtraction of the 2x is insignificant, and so we just, instead of saying 0.25 minus 2x, we'll just say 0.25. And then we use the approximation to help us quickly find what the value of x is. We perform the two checks to make sure that the 5% rule works out and Q is approximately equal to K. And then with our x value, we can then state the equilibrium values. Okay, for the next question, I'll get you guys to do that on your own. However, if you'd like to check to see if you got the right answer, I will give you the equilibrium values. And so the equilibrium values, these are the answers. NaCl at equilibrium is approximately equal to 0.40 molar. The concentration of nitrogen monoxide at equilibrium is approximately equal to 0.0172. Okay. And the concentration of Cl2 at equilibrium is approximately equal to 0.00862. Okay. So those are the assumptions that, or rather, these are the answers that you can make, that you can get using the assumptions that you will make in the question. Great. Thank you for watching.